Okay, I'd like to welcome everyone and thank you for joining us. I'm Gloria Palmer, the Executive Director of Green Mountain Academy for Lifelong Learning. Today's presenter is Valerie Rapson. She is an astronomer and public outreach enthusiast who enjoys teaching people of all ages about science. A native of Rochester, New York, she earned her PhD in astrophysical sciences and technology at RIT, where her research focused on the chemical composition and structure of planet-forming disks around nearby young stars. Prior to joining the faculty at Oneonta, Dr. Rapson was the director of the Dudley Observatory in Albany, New York. She is a National Astronomy Ambassador and was awarded the 2018 Emerging Leader Award by Girls Inc. of the Greater Capital Region for being a role model to young women who aspire to become scientists. It's really wonderful to have you back with us, Valerie. Thank you.
Yes, thank you. It is really great to be here. Just a quick question. Who came to my talk a couple of years ago about Mars? Was anybody at that talk? A few hands there. If not, no big deal. I was just curious. I had visited you guys a couple of years ago in my job at the Dudley Observatory. But today we're going to talk a little bit about the Hubble Space Telescope. So let me share my screen here with you guys. So as Gloria mentioned, my background is, of course, in astronomy, but it's not particularly with the Hubble Space Telescope. I've only worked a little bit with the Hubble Space Telescope, some of the data that came back. I'm not, directly part of the mission team or anything like that. But the Hubble Space Telescope is such an iconic instrument that I thought it would be fun to talk about it today. Especially since they just celebrated their 30th anniversary back in 2020, and they had planned, all of these events around it, all this cool online stuff. They were going to send scientists all over to give talks. And of course, what happened in 2020. So they've kind of pushed things back a little bit, and they're celebrating the 31st anniversary as if it were the 30th anniversary of the Hubble Space Telescope. So we just kind of cross out the 0 and stick the 1 there. That works too. But today's lesson is basically just going to give you an introduction to the Hubble Space Telescope. What is it? Why is it important? What are some of the things that it is able to observe? And then the second half of the presentation is going to be fun and interactive, where I'm going to show you some pictures that the Hubble Space Telescope has taken of objects in outer space. And I'm going to have you guess what the pictures are of before I actually share some information, because some of the images from Hubble are pretty obvious and others are not so obvious. So I think it's kind of cool to actually stop and think about what you're really looking at, not just being in awe of what you're seeing in the image in space, but just thinking about the science behind it as well. So that's the plan today. And as Gloria said, feel free to stick things in the chat box. When we get to that portion of the program, I'll give you a little more information there, but don't be shy about asking questions or putting information in the chat box. All right, so let's get started with the basics. The Hubble Space Telescope was the first of NASA's 4 great observatories. So back in the 1990s and early 2000s, NASA had planned to send 4 large telescopes out into space, and Hubble was the very first of those telescopes. You can see a little cartoon of the 4 different telescopes here. Hubble is shown here, abbreviated HST, and you can see a real photo of it in outer space on the right-hand side. The other 3 great observatories are listed. This is CGRO, the Compton Gamma Ray Observatory. This is the Chandra X-ray Observatory. And SIRTIF has the more common name of the Spitzer Space Telescope. And the main difference between all 4 of these and why we needed 4 space telescopes in the first place is because they all observe different types of light. So Hubble was designed to view the universe in natural light, basically show us what our eyes can see if our eyes were as large as the optics of the Hubble Space Telescope. So I think that's why people connect with the Hubble Space Telescope so much. I mean, in part because it has been up there for so long and sent back so many beautiful pictures. But Hubble is seeing what we are able to see. Some of the images from the other space telescopes can look a little strange or odd because we're not seeing the light that our eyes can see. So the images don't look quite as recognizable. But for Hubble, we recognize a lot of the images right away. Now, the Hubble Space Telescope, of course, was named after Edwin Hubble, an astronomer from the early 20th century, arguably the most or one of the most important astronomers He made all sorts of amazing discoveries about our universe, including the fact that galaxies are actually objects outside of our own Milky Way galaxy. So great astronomer, definitely deserves to have the spectacular telescope named after him. Let me show you a little bit about the design of the Hubble. What does it look like floating around in outer space? So here's a cartoon of Hubble with a little bit of the side pushed away there so that you can see what's on the interior. Basically, Hubble is a big silver tube that orbits around the Earth. So the main telescope is the skinny tube on the top. The bottom is where the instruments, including the cameras and computers and all of that, sit at the very bottom. It is powered by solar panels, so you'll see 2 solar arrays in the picture. The light comes in from the front, so you want to point the front of the telescope towards what you're looking at. Light will come down the tube, hit the optics, and ultimately be sent down to the back of the telescope where the light is registered and the picture is taken. There's also a little cover on the front. This is a solar shield that can be opened or closed, depending on where Hubble is in its orbit and how it's oriented. Sometimes it'll be tipped a little bit towards the sun. And the last thing you want to do is take all of the concentrated light from our sun and send it down this very sensitive instrument. That would not be a good day for the Hubble telescope. So it has a little cover that can open and close. And of course, there are communications antennas, right? We don't go up to Hubble and, grab a thumb drive out and bring it back to Earth. We just send things down via radio signals through the antennas. The size of the Hubble primary mirror is shown on the right. So Hubble has an 8-foot or 2.4 mirror. So it's shown here, average height of a human. So not much taller or wider. Well, I guess a lot wider, but not much taller than the average human being. And to give you a sense of the length of Hubble, I like this comparison. The Hubble Space Telescope itself is about the length of a full-size school bus. So the next time you see a school bus driving by, you can think of the Hubble Space Telescope. That's as big as it is. Now, we mentioned that Hubble observes primarily in natural light, visible wavelengths of light, but it also has the capability to look slightly in the ultraviolet and slightly in the infrared, which is types of light that our eyes cannot see. But it's designed primarily to look at that visible range of light with a little bit on either side. So you will see some UV and infrared data in the pictures that I show later on. So Hubble was launched in 1990. It was actually originally planned to launch 4 years prior in 1986. But you may remember one of the terrible things that happened in 1986, the Challenger disaster in January of that year. So once that happened, the launch of the Hubble Space Telescope was placed on hold. The engineers and the astronauts and everybody wanted to make sure they understood what happened with Challenger because we didn't want to risk any more astronaut lives. So they put the launch of the Hubble telescope on hold, and ultimately it went up April 24th of 1990 on Space Shuttle Discovery. So you can see an actual photograph of Discovery on the rocket boosters there, and this was during the launch of Hubble. So you can't see it on the inside, but Hubble, I promise, is underneath or inside of the shuttle there. And the picture on the right is a really cool image. This is basically a picture. You can imagine it like there's a camera on the back fin of the shuttle there, and it's taking a picture of this bay, which the 2 doors spread out, they open up, and there's an arm that can lift the telescope out of the shuttle and essentially let go of it in Earth's orbit. So the Hubble Space Telescope was placed in Earth's orbit in 1990, and it has been functional ever since. It's been a really fantastic observatory. So I mentioned that Hubble is orbiting Earth. It's technically in what we call low Earth orbit, which is about 353 miles up. So you can just kind of go outside and look up, and 353 miles above your head is about where the Hubble Space Telescope flies over. Now, its orbit around the Earth, it does not line up with the equator or the poles. It's actually tipped a little bit, and you can see that in the cartoon. Here is Earth. Earth's equator is the blue line, and the approximate orbit of the Hubble Space Telescope is shown in yellow. And what's cool about this orbit is that it allows the Hubble Space Telescope to see things in both the northern and southern hemisphere. So it can see things in the northern sky as well as the southern sky. And you can see that its orbit passes directly above Florida in this cartoon. And that means that in general, when you're in the United States, you can occasionally see the Hubble Space Telescope in the sky. So I'll tell you more about that in a moment, but its orbit does allow us to actually see it as one of the satellites in the sky. Now, Hubble goes around the Earth once every hour and a half, roughly, which means it's flying by at 17,500 miles per hour. All of the satellites and telescopes that are in orbit really whip around the Earth compared to speeds that we're used to. And the reason that we put Hubble so close to the Earth compared to sending it farther away in space where some other telescopes are, is so that it could actually be serviceable. So astronauts using the space shuttle used to go up and fix the Hubble when it needed fixing or replace the instruments. The astronauts actually started training in 1979 and then serviced Hubble all the way up through 2009, shortly before the shuttle program was decommissioned. So one thing I'm just remembering that I forgot to mention in the last slide with these dates here of 1979 and being launched in the 80s and 90s, we have to remember the type of technology that we had at the time, cameras and things like that. Because I'm going to talk about, maybe you heard it in the news, there was a little glitch with Hubble recently, and it just kind of helps to remember that a lot of the technology in the hardware, the computers there, is from the 70s and 80s. It's not modern day stuff necessarily. So anyways, we'll come back to that in a bit. But if you want to check out when you can see the Hubble Space Telescope above your head, you can go to this website called heavens-above.com. It's a really nice website that a lot of astronomers use to figure out what kind of cool things they can see in the sky that aren't the stars. This is really meant to show you comets and satellites and other things that are not the classic stars to see. And I went ahead and I just checked to see if you guys could see it. I put Bennington, Vermont into the list, and this is what came up. So Hubble will be visible very low in the sky, but on August 28th and 29th, if you're an early riser, we're talking 4 or 5 a.m. local time, if you have a really good view of the southern sky, you can see a little bright dot just kind of passing just above the horizon for a minute or so, right around 5 a.m. both days. Now, if you're not an early riser, don't worry, you can check out that website. Hubble will be passing over many different times at different hours of the night. These just happen to be the two upcoming ones this week. So when Hubble was launched, obviously it was designed to look at the stars. And I wanted to show you the very first picture that Hubble ever took, because I'm sure many of you know that Hubble had a few issues when it went up the first time. So here we have two images. These are pictures of just a star cluster in the sky. It's an open star cluster. It has a catalog license plate number for a name, NGC 3532. Basically, there's 5 stars in the picture. 2 up here, 3, 4, and 5. And the image on the left is actually not from the Hubble Space Telescope. It's from a ground-based observatory. And you can see from this picture here that the stars are not super crisp. The resolution isn't great. The images are kind of pixelated, which is what we expected at the time for ground-based observatories. That's why we built Hubble. We wanted to get above the atmosphere and get nice crystal clear images. So the picture on the right-hand side was the very first image that the Hubble Space Telescope took of the same exact region of the sky. And you can see the stars a little bit better. You can see that there actually are 2 blobs at the top for stars, the star here and small ones down here. But the image really wasn't what we expected. We were expecting nice, crisp circles and bright dots for our stars. With this telescope, there should be no blurriness. There shouldn't be anything wrong with our images. But the image on the right has some pretty obvious problems. If you look at this star, for example, it looks kind of squished. It's really not round. And the 2 stars on the bottom here, they have this optical effect called coma, where the stars end up looking a little bit like comets, where one side is really bright, and then they have this like extended tail on the bottom. And you can see that there's like a little bit of fuzz of light that seems to travel down below. So the first images that came back from Hubble signify that there was definitely some issues. Something was wrong. The Hubble Space Telescope wasn't acting as perfectly as they intended it to be. So after looking at this a little bit more and trying to figure out what the heck was going on, astronomers realized what the problem was. They realized that the telescope was showing what we call spherical aberration. The images were blurry, and this is caused when the curvature of the primary mirror inside of the telescope is not curved exactly right. Or if you think about it, when you're grinding the mirror, you have to polish it and grind it down to the perfectly curved shape so that everything comes to a focus in the right way. If you don't have that curvature just right, if you don't grind it just the right way, then you're not going to have a nice, crisp, clear image. So the primary mirror of the Hubble Space Telescope was actually ground a little bit too thin. And that's what this cartoon tries to show here. So the actual shape of the mirror is this curve in red, and the intended shape is a sort of a light green color here. And you can see that it's slightly curved a little bit more, or it's slightly curved a little bit less than it should be. And if you zoom in, you can see it's 4 microns too flat, 1/50th the thickness of a sheet of paper too thin. So even that small little error at the edges of the mirror basically destroy your image. Now, to show you what happens, the images, when they hit the mirror that's not curved properly, the light doesn't end up focusing all in the same spot. So what you're looking at here are 2 cartoons where we've placed an imaginary Hubble Space Telescope mirror at the bottom. The light comes in from the top, bounces off of the mirror, and depending on where it hits the mirror, it's going to be angled, and it should all come to a focus in the same spot. That'll give you a nice, crisp image. But the Hubble Space Telescope, unfortunately, didn't do that. With the edges too thin, as shown on the right, the light on the edges basically focused a little higher than the light at the center, and that elongates and that blurs your image. Exactly what we just saw in the previous slide. So this really stinks, right? We didn't spend all this money on a Hubble telescope to have it not work right. And I want to show you the 2 galaxy pictures a little bit bigger there so you can really see the problem. The image on the left is a picture of the galaxy before the Hubble was fixed, and the image on the right is afterwards. So I think this picture really shows, the potential that the Hubble Space Telescope had and what we had started with in the very beginning. So thankfully, we were able to fix this, right? And the only reason we were able to fix it is because Hubble was in low Earth orbit, which is kind of crazy because nowadays we put so many telescopes a lot farther from Earth in places where they are not serviceable. And basically we cross our fingers and trust the engineers that they did an excellent job and that we won't have any issues. So we're very lucky that the large space telescope that had the issue was the one that we were actually able to send astronauts up to fix. So that mission to fix it came a couple of years later. It took them some time to figure out what the issue was and exactly how to fix it. But in December of 1993, some astronauts went up on the space shuttle via Endeavour, and they spent 5 days fixing Hubble. And the way they fixed Hubble was they basically gave it glasses, right? If our eyes are broken, we generally don't have surgery in our eyes to fix the curvature of the inner bits. We just put on a pair of glasses or a pair of contacts. And that was the easiest way to fix this telescope. It wasn't practical to send a new primary mirror up into space and replace the old one. All we had to do was basically give Hubble glasses, add some optics to the system to be able to fix the image. So that's exactly what they did. The picture on the right is a real image from the astronauts in the shuttle who had latched on to Hubble, and they are putting in COSTAR, the Corrective Optics Space Telescope Axial Replacement System. We call it COSTAR for short, but basically it's the glasses for Hubble. And once inside, the light that hits the primary mirror would pass through COSTAR. The optics on the inside would correct the image, and then it would feed that corrected image to the cameras and all of the instruments that were in the back of the telescope. So this was the first repair mission to Hubble, and they put in COSTAR and they also put in a new camera. By 1993, the advancements in digital photography had increased so much that it was really time to replace the digital cameras that were from the early 1980s. So they were able to do that on this mission as well. Now, in future missions, they kept increasing the quality of the instruments and changing them out. And by May of 2019, they had actually replaced all of the instruments, and subsequent instruments basically had corrections built in. So CoStar was no longer needed. The glasses were built into the individual cameras, and we didn't need that initial pair of glasses out front. So that was removed in the last mission in May of 2009. So I'm not going to go into all the details of the service missions. We'd be here all day. But I just wanted to show this graphic to give you a sense of the types of things that were fixed and the improvements that were made to Hubble over the years. So we had the launch in 1990, the first service mission to fix Hubble in 1993. They added in CoStar and a new camera. They had also put the solar arrays on, and they put in some new gyroscopes. Gyroscopes are used to position the telescope. They spin inside, and by spinning them at just the right rate, we can actually accurately point the telescope. Second service mission was in 97. They added a near-infrared camera and a spectrograph, along with a fine guidance sensor to allow the telescope to point more accurately at the objects. 99, there was another upgrade to the gyros and the computer, a new fine guidance sensor. 2002, they added a cooling system for one of the infrared cameras, updated solar arrays, a new power control unit. And then in 2009, they knew that the shuttle was probably going to be decommissioned shortly after that. So basically, they did everything they could possibly think of. They were like, okay, how can we make this telescope last as long as humanly possible? So they replaced as many parts as they could. They put up some backup systems, added new batteries, put state-of-the-art cameras and equipment in there. Whatever they could do, they did to make Hubble hopefully last for as long as possible. So that's kind of the timeline of all of the service missions. And now that the shuttle is decommissioned, there will be no more service missions to Hubble. If Hubble breaks, we will go up to Hubble, bring it back down to Earth, and likely just let it burn up in the atmosphere. So we're going to cross our fingers that Hubble stays mostly functional for at least a few more years, because we'd love to get some more data from it. So to kind of wrap up this first part here, I just want to give you some numbers, which continually change day to day. So these are as up to date as we can get. The total cost of Hubble was pretty expensive, but we have to remember, what all of this money went into and what it actually covered over the years. So Hubble has cost us over $10 billion, but that includes the construction and the launch back in the 80s and 90s. That includes all of the service missions. That includes paying all the scientists to control and monitor Hubble for the last 31 years. And it includes some of the funding that is given to scientists to analyze the data. So $10 billion is a lot of money. Don't get me wrong. I don't have $10 billion to waste, but we have done an incredible amount of science with $10 billion in the Hubble Space Telescope. We saw that there were 5 servicing missions. Hubble has orbited the Earth so much that it has traveled over 3 billion miles if you add up all of the orbits around the Earth. And as I mentioned, a lot of science and a lot of data comes back from Hubble. Nowadays, we get about 150 gigabytes per week of data. And in total, it has taken over 1.3 million pictures of things in outer space. And there have been over 15,000 scientific papers that utilize the data from Hubble to discover something new about space. So really, in my opinion, money well spent on this telescope for sure. And now that Hubble has been fixed, the optics are repaired, I wanted to point out how precise this instrument is, especially for its time, because you got to remember it was designed in the 80s. The resolution, the quality with which you can see an object is equivalent to being able to stand in Washington, D.C., looking across the Earth, the distance of Tokyo, Japan, and being able to see 2 fireflies as long as they're at least 10 feet apart. That's the resolution of Hubble. So 2 fireflies 10 feet apart in Tokyo, Japan, go all the way to Washington, D.C., assuming you can actually see over the curvature of the Earth there. And you'd actually be able to point Hubble at those fireflies and see the 2 individual fireflies 10 feet apart. which is pretty darn amazing in my opinion. So Hubble is amazing. It has sent back so many lovely pictures, done some great science, and I'm sure that many of you have seen a lot of the spectacular pictures that have come back. So now we're going to transition into what I think is the more fun part of the talk here. It'll be a little bit more interactive. So in 2020, the Hubble team released a calendar and all sorts of pictures. And one of the sets of images that they released was called the Hubble Hidden Gems. These are real photographs that were taken by the Hubble Space Telescope, but they aren't necessarily the classic stereotypical pictures that have been in the newspaper and in all the astronomy magazines. So while you may have seen some of the images that I'm going to show you, a lot of them I think will be new. And a lot of them have some really cool science associated with them. So I thought it'd be fun to kind of go through these pictures and look at them and just be in awe of how beautiful they are, but also talk about the science behind them. Because maybe if you weren't visiting this talk, you might not ever see these images. So as we do this, I thought it would be fun to play a little game that I call What the Hubble Is It? And the way we're going to play this game is I'm going to start with each slide and I'm going to show you a picture. So here is a real Hubble Space Telescope picture. And I'm going to have you guys, either you can unmute and say your guess, or you can type it in the chat box. I want you to guess, what do you think we're looking at? And I'm going to give you some generic things. I don't expect you to know the name of the object or anything specific about it. I'm thinking like, is this a picture of a planet? Is this a star cluster? Do you think it's a star-forming cloud, a dead star, a galaxy? Or do you have no idea? Because some pictures you're like, what in the world is that blob on the image? So that's kind of what I was thinking here. So we can practice it. This one's kind of easy. So what do you think you're looking at in this picture? You can type your answers in the chat box. You can feel free to unmute. Who wants to take a guess? What are we looking at here?
Dave
and they're
and
not
Jackie
really intended to be tricks. Oh, I'm sorry. Say that again.
Dave and Jackie say star cluster.
I have a vote for star cluster. Any other guesses?
Galaxy.
Oh, we have a guess for galaxy. Nice. Yeah. See, this is what I like, is I want you to kind of guess and think about it here. And if you don't feel like sharing, that's okay too. You can kind of guess in your head. So this is indeed a star cluster that we are looking at, and it is in our own galaxy. So whoever said galaxy, that works too. But this is basically just a star cluster, and we can take a look at the different colors in the image and see that there's a lot of blue stars, red stars, and white stars scattered about. And that tells us something about the temperature and potentially the ages of the different stars there. So that's how we're going to play the game. I've got a whole bunch of pictures to go through, and I'll keep an eye on the time so we're not here all night long. But I think you're going to really enjoy some of these images coming up. So we're going to start with the picture that was actually on the front of the calendar there. Here is that picture. So the name of the object, by the way, if it's not an easy giveaway name, will be up here. Just another license plate number for a name. What do you think we're looking at here? What type of object do you think this is? Anybody want to?
Galaxy.
Sylvia says galaxy.
What are you guessing? Stars being formed in a gas cloud.
Ooh, star formation in a gas cloud. Would you believe that you're both right? It's a galaxy and there's a ton of star formation going on. So this one is indeed a galaxy. We are looking at a separate galaxy outside of our Milky Way, but it's a really special galaxy that we call a starburst galaxy. Starburst galaxies generally occur when you have two galaxies that collide with each other in outer space, and a lot of the gas and the dust literally hits each other. It compresses, it gets hot and dense, and it triggers pockets of star formation. So when you look at this image, you can see sort of a spiral galaxy structure here, but you see some additional arms. And you also see these little dark pockets here. Those are clumps of dust and gas where the star formation is actually happening. Now, we can see the clumps of dust, so we can assume that star formation is happening, But those wispy spiral arms around the outside, those are what we call tidal tails. Those are direct signatures of two galaxies interacting. If you imagine two galaxies with big spiral arms kind of hitting or passing by each other, the gravity is going to start to pull on their spiral arms and start to tear them apart. So we see that interaction here. We see these tidal tails where the gravity is starting to pull the galaxy apart. So this galaxy happens to be 100 million light years away. We talked about the pockets of gas where the stars have formed. And to put the nail in the coffin that this is indeed a starburst galaxy, some astronomers actually took a look at the very center of the galaxy here with a different type of telescope. They took an infrared image of the center. And when they looked at the center of the galaxy, they saw not one object in the middle, but two. So this galaxy has what we call a double nucleus, essentially two supermassive black holes right next to each other, probably from a literal collision of two galaxies whose black holes are about to spiral around each other and combine into one. This is a really cool galaxy with a lot of science literally embedded inside of it. And using Hubble combined with other telescopes, we can learn a lot more about these galaxies. So very good. You got this one. This one's a galaxy. Let's try this one. What do you think you're looking at here? Is this another galaxy, stars, clouds? What do you think?
Your guess, Jack? Yeah, we think it's a gas cloud.
Another gas cloud. Any other thoughts? So this one is really cool.
Sorry.
Oh, go ahead. No, I heard galaxy. Yeah.
I was going to say galaxy unforming itself or coming apart.
That's a really cool idea. And I can kind of see why you might think that, right? If we've got like a central galaxy here and some weird things happening above and below. So this one here is actually not a galaxy, and it's sort of a gas cloud, but not really. This is what we call a planetary nebula. It's actually a dead star. So a star like our sun eventually will end its life. And when stars end their lives, they puff up, and the gravity inside is not able to hold the outer layers of the star together. So the star actually releases its outer layers and creates this new cloud of what was the plasma of the star. So what you're seeing here is a planetary nebula, which is the leftover bits of the outer shell of a star that have been released into space. The name is a little misleading. They don't have anything to do with planets. They're called planetary nebula because originally they thought they might be fuzzy planets, or they look like fuzzy planets in telescope pictures, but we now know that they are dead stars. So this here, what you can imagine is the star was somewhere in the middle, and it kind of released material above and below into the side. So you're seeing basically episodes of mass loss, chunks of material being blown away into space. Now, if a star like our sun, which is a sphere, a round object in space, you might imagine that when that ends its life and sheds its outer layers, it should make another circle in space. But when you look at this, it looks a lot more disastrous than a sphere, a circle. So this kind of S shape here is common in planetary nebula. And we think what's happening when we see this kind of lopsided S shape in the nebula is that there's actually a companion star. You can imagine a star like our sun that is dying and shedding its outer layers. And if there's a second star orbiting around it, the gravity from the second star will actually tug and toss some of the material in other directions. And that can kind of create this spiral or this S shape that we see. So this is a really great example of a binary, a two-star system where one star is dying and the second star is just tossing some material on either side. It's believed that the second star is probably already dead and maybe even contributed to some of that material that we see in the picture. All right, so we saw a galaxy, we saw a dead star. I think this next one is pretty obvious. I think you all know what this one is. Who wants to tell me what this is a picture of?
It's obviously Saturn.
Yeah, right. I didn't put the name there because that would be a giveaway. So Hubble did look at the planets, and this is a really nice picture of Saturn. Hubble wasn't specifically designed to observe the planets in our solar system. It was designed to look at things much, much further away. But it did have the ability with certain instruments to look at the planets. And what you see here is the beautiful ball of Saturn. You see the big ring structure. And the dark line there, that's the Cassini division, basically a very low density region where there's not a lot of ring material, so it looks dark in the pictures, even though there is a little bit of material there. But just a really spectacular picture. And you can see around circled the labels there. Those are 4 moons that also happen to be visible when Hubble took this picture. And I'll show you them up close for a second. The pictures of the moons did not come from Hubble. They came from the Cassini mission, which flew to Saturn and orbited Saturn for like 14 years. But the moons look really cool, so I have to show them to you. That's Enceladus, an ice-covered moon that likely has a subsurface ocean and maybe even life. Janus is kind of boring. It looks like a little asteroid, a rock. It's quite small. Tethys is over here, more spherical. It's got some really big craters. And then Mimas is particularly interesting. If anybody is a fan of sci-fi movies, does Mimas look familiar to you? If I put up this picture, does it help?
The Death Star.
Yeah, it looks like the Death Star from Star Wars. So NASA has actually had to clarify this multiple times. Star Wars and the imagery of the Death Star was created about 5 years before we had ever seen what Mimas looked like up close, and long before we had these Cassini images of the real details of Mimas. So a lot of people were like, oh, they modeled the Death Star after this moon of Saturn, but it's actually just by chance that the moon of Saturn looks like the Death Star. So they're not related at all. It's just funny that they look that way. And on the moon, this is actually a really large crater where a large asteroid struck the moon at some point in the past, and basically left a big hole inside. So Hubble can take some really cool pictures of our solar system too.
I have a question.
Yeah, go for it.
In the last slide, in the lower underneath Janus, it looks like there's an arrow for north and east.
Yep.
How can there be direction in space? North and east from where?
Yeah, that's a great question. So we define north and east as we would here on Earth. So if we were looking at Saturn from Earth's perspective, how would we orient the image? So that is north up from Earth's perspective. And we define like the north and south pole of a planet in the same direction as we define the north and south pole of Earth, even if the planet is tilted a little bit. So it's really defined from Earth's perspective, not from the planet's perspective. It's a great question. All right, how about this one? What do you think you're looking at here? Any guesses? This one's kind of peculiar.
Looks like another nebula.
Yeah, let's find
Floating
another
star.
nebula. Yeah. The nebula is exactly what astronomers thought this was until they watched it over time and looked at it more closely. This is a very weird one. And just showing you one picture honestly doesn't do it justice. So I'm going to explain to you what this is, and I'm going to show you multiple pictures. So this is a nebula in a sense that this is a cloud of gas and dust. And there is a really bright reddish colored star at the center of the nebula. But what you're physically seeing in the picture here is something called a light echo. So what we believed happened is this red star, it's kind of embedded in that nebula there. That is a supergiant star. It's a star very massive that has reached the end of its life. And it went through an outburst. So these stars, what happens is they go through this very rapid expansion. And when a star gets really, really big, it gets very bright, very fast, because the bigger your star, the more surface area and the brighter the star is. So this star brightened from its normal brightness to literally 1,000,000 times the sun's luminosity, just very, very quickly. We're talking months' time. That light then left the star, and the light illuminated all of this nebulosity around the star that wasn't known before the picture. So let me show you like sequential pictures here. Here we have images all from Hubble from May of 2002 up to February of 2004. In each one, the red star is at the center. That's the star that emitted this glow of light. And basically what you see happening is the glow of light travels outward. It illuminates this inner circle. It travels outward, gets bigger and bigger. And initially, astronomers thought that what they were seeing was material leaving the star. They thought, okay, it just released this material. We're watching the material move outward. But that's not what we're seeing. We are seeing light travel outward, not material. And the light is bouncing off of a cloud that was already there. So in this picture, in the very first image in the upper left, all of this brown material is there on the outside. We just can't see it yet. We actually have to wait for the light to travel outward farther and farther until it reaches the edges of the nebula and lights it up for us. So this was one of the first and most obvious examples of a light echo that we have ever seen in space. Instead of material traveling outward, we're watching light travel and illuminate material that we didn't know was there. It was really, really neat. So Hubble took a ton of pictures of V8381 because they wanted to see how this light echo was going to progress. If you looked at it today, by the way, you would see just a red star and not much else because the light has continued to travel and the material here doesn't glow anymore. So we would just see what looks like a boring red star.
Question?
Yeah, go for it.
What is in the final picture? What is the diameter of what we're seeing?
Oh, that's a good question. I don't think I have that number off the top of my head. But my guess, usually for these types of things, we're talking light years scale, at least a few tens of light years. So this is really, really large compared to the size of the star. So many times greater than our solar system. I should have put a scale bar there. All right, so this one is kind of could give it away a little bit because it has it in the name here. So I'll tell you what this one is, and then we're going to look at why it's called the Tarantula Nebula in a second. So this is a nebula, basically a cloud of gas and dust. And in particular, this is a star-forming nebula. So we can have the clouds of gas and dust that are the leftover bits of a dead star. But we can also have the nebula where the gases are collapsing in and creating new stars. So you're seeing star formation in this picture. This nebula is part of the Large Magellanic Cloud, which is a tiny galaxy in the southern hemisphere that is orbiting around the Milky Way. So we actually have satellite galaxies, very much how like the moon is a satellite of Earth and orbits around the Earth. A satellite galaxy is a baby galaxy that orbits around the Milky Way. So this cloud is in the Large Magellanic Cloud, about 160,000 light years away from Earth. And it's the most active star-forming region that's associated with the Milky Way. So we're seeing lots and lots of star formation occurring here. And this is actually the site of the very famous supernova 1987A. So you may have seen pictures like this before. That was early imagery before Hubble of supernova 1987. So it was a massive star, died and exploded, illuminated some outer layers of material that had already shed. And basically the star exploded in 1987, and we can still see some of the remnants of it today. But that's one of the early on pictures before Hubble. It's really a shame that Hubble didn't launch in 86 like it was supposed to, because it would have been able to get the most amazing pictures of the closest supernova to ever happen to Earth. And that's what this one was. So we missed it by a couple of years, unfortunately, but maybe we'll get to see another one soon. Now, the Tarantula Nebula, I'm going to go back for a second here. You might be wondering, like, where do these things get their names? Because that doesn't look like a tarantula to me, but we call it that. So a lot of these names, they don't necessarily come from Hubble imagery. They come from early observations. We're talking, 100 years ago, somebody looked at this and thought it was a tarantula. Or maybe we're looking at more modern imagery and we're just trying to, use our imagination and piece it together. So I did have a little fun earlier. I was looking at pictures of this. So here's another space telescope image of the same nebula, slightly different colors and filters, so it looks a little different. But I thought for a moment we could try and imagine a tarantula inside of it. So if you don't like spiders, close your eyes for like 30 seconds because I'm about to put a picture of a tarantula on the screen. So if that freaks you out, close your eyes. But here comes a tarantula, just in case you don't remember what they look like. And then I was like, okay, if I'm going to figure out what this looks like maybe that's the tarantula that we see. I tried to envision, you know, the arms and the legs, or maybe it's like this, you know, I'm still trying to match up the lines and the patterns to the body of the spider. But the point here is that you see these colloquial names and they don't necessarily look like what we see in the sky, right? And this happens for constellations too. You know, Cancer the crab, I guarantee you cannot connect the dots and make a crab in the sky for that constellation. It just doesn't work. But they often come from, you know, early sightings or somebody just gave it a fun name over the years. So for this one, we are stuck with the Tarantula Nebula, even though it maybe doesn't look so much like a tarantula. All right, picture of a spider gone. If that was freaking you out, the spider's gone, it won't come back. So what about this one? This is a really cool picture. And this was not photoshopped. It wasn't two things put in the same spot in the sky. These two objects here and here were actually there in space. Any idea what's happening here in the cosmic reef? Anyone want to guess? It does kind of look like a reef. So what we have here, we have another nebulous cloud, another star forming region. And you can tell that they are distinctly two different colors, right? The big cloud over here is red, and obviously the cloud in the bottom left is blue. So these star forming regions also in the Large Magellanic Cloud in our southern hemisphere, the colors tell us something about what's happening. So in the cloud here, the red coloring is really highlighting hydrogen and nitrogen, which is generally a little bit colder. The material is condensing down and really starting to trigger the star formation. And a lot of these blue stars might be stars that are forming inside that nebula. Now down here, it's clearly all blue. We've got something else going on. The blue highlights oxygen. And usually we only get oxygen glowing blue like this when the temperatures are really high. We're talking 20,000 degrees Fahrenheit high. So what's actually happening in the little blue nebula there, that is actually a young but massive star that has already lived through its life, even before all the other stars in the nebula here have formed. So the star in the center has ended its life. It is blowing away its outer layers. And the star was so hot and powerful in its explosion that it's literally ionizing and causing all of this material to glow super bright at blue wavelengths that is surrounding the evolved star. So colors in these pictures, they do represent what our eyes can see, meaning that oxygen might look a little blue and hydrogen might look a little red if we could see like the Hubble. And we can use the coloring, we can use the filters that are on Hubble to learn about what's going on. So the colors really do mean something here. They tell us chemical composition, but they also give us a clue to temperature and help us understand where the cool material is to form the stars, where the hot material is, where stars may have already died and have winds that are blown away into space. So all sorts of neat things happening here. And I just love this picture. It looks like somebody photoshopped the blue thing next to the red thing, and that's just naturally in space how these are.
Question.
Go for it.
How much oxygen is there, say, compared to what's in our atmosphere?
Yeah, not a lot. I mean, if you were to total up maybe all of the oxygen in this nebula, it would be quite a bit. But when we think about like densities in outer space, even in these nebulas, you still are essentially a vacuum. So the level of oxygen is very, very low, a lot lower than the oxygen, a lot lower than the levels of oxygen in our atmosphere. So we do see oxygen throughout outer space, but it's in incredibly low densities compared to Earth. Otherwise, we'd have planets all over with oxygen and maybe life, but I don't think that's the case, unfortunately. All right, this one is one of my favorites. It definitely looks like a stellar explosion, but it's actually another example of star formation. And this one is really neat because you're not looking at it the way you think you're looking at it. So what you see here is actually a young star. It's about 15 times the mass of the sun, and it is actively collapsing and forming and spitting material out the poles. So it's going to help if I show you a cartoon of what we think we're looking at here. So this is what we think we're looking at. Basically, you have clouds of gas and dust that collapse down, and that young star starts to spin. The spinning of the young star causes a disk of material to form around the star. So you've got a baby star in here, and then this disk of gas and dust around the outside, and that's where planets are going to form. The material will stick together and make a planetary system. So we think we're seeing this happen edge on. So here's the side of the disk in the picture, and the young star is buried somewhere in the center there. And we have jets that are blowing out the north and south pole, or the top and the bottom of the star. And that's what this blue material is here. So basically the star is spinning, it's flattening out some material into a disk, and that rotation is causing these jets that continue to push some material just away from the system. So you're literally seeing star formation in action here. And it's not just, one tiny star embedded in the nebula. This whole entire picture is a single star that is forming inside the nebula. It's very rare that we get pictures like this where we're seeing the disk and the jets, and then maybe with an infrared telescope, we could spot the star all in one picture with this kind of detail. Normally all we get are just little red dots, and that's not super exciting, but this is like all the details combined into one. So this system, it's going to take a little while, probably a few million years more, but it will eventually form planets, potentially a system similar to our own. All right, what do we think this is? This one's kind of obvious. What does this look like?
Galaxy.
Yeah, this is a galaxy, NGC 634. And this one is actually dubbed the perfect spiral galaxy. That's its nickname. So galaxies can have a whole bunch of different shapes. You're going to see that in the next slide, or in the next picture. But basically, this is a spiral galaxy. So you've got gases and dust and stars that have flattened out into a disk. There are big spiral arms around the outside, and usually a supermassive black hole in the center. So our Milky Way galaxy probably looks something like this, with the spiral arms around it. And this one is just like nice and tightly wound. You can see the arms really well with a bright center. And I wanted to point out, or use this picture to point out, that Hubble can do some really cool things, include providing images that we can compare with both past and future pictures to see if anything changed. So this is a great example of a galaxy where we did observe a supernova, a star that died and exploded in the galaxy. And then 2 years later, Hubble happened to look at the galaxy, and we can see that the supernova is gone. So let me show you here. I'm going to flip the picture to show you a comparison directly. So this picture here is going to do a horizontal flip upside down there. And that way we can compare it with this picture from 2 years prior, 2008. So it's not a Hubble Space Telescope picture, which is why the galaxy's tiny. But there's the galaxy. These two stars here are these two stars in the picture. This bright star right above my red dot is this bright star here. And you can see in the picture in the upper right, there's another dot just below the spiral arm. That is a supernova. And you definitely don't see it in this picture 2 years later. So these supernovas, they last usually for only a month or so, not very long. They get really bright. Sometimes they even outglow the galaxy. And then they fade away over a month's time. And definitely by 2 years into the future, they disappear completely from our sight. They're just too dim to see. So we spot supernovas in other galaxies constantly. We pick up hundreds of these in a year's time. And telescopes like the Hubble, again, make for really great comparison pictures. Sometimes we can even go back and try and figure out the exact star that exploded if we have a before picture from the Hubble and an after picture that shows a supernova. So sometimes we can go the other way, which is really helpful for astronomers. Now, speaking of different types of galaxies, this one is obviously galaxies. It's one of my favorite pictures that Hubble ever took. It's called Stephan's Quintet. It's 4 galaxies. And this really exhibits the different types of galaxies that exist in our universe. So you can see 1, 2, 3, 4 galaxies, and none of them look the same, right? You've got this one here, which is maybe what your brain classically thinks of as a galaxy. Bright center, spiral arms, kind of blue. The other 2 are more yellow. The blue tells us there's a lot of star formation, a lot of hot blue stars. The yellow coloring says that the star formation is starting to fade away. The galaxy is probably older. These 2 have a bar across the center. Don't know exactly why these galaxies form bars, but they apparently do sometimes. This one does not. It's kind of perfectly circular. And then the little fuzzball at the bottom, this is a totally different type of galaxy, an elliptical galaxy that is very old and does not have any spiral arm structure. So this just exhibits all of the different types of galaxies in one gorgeous picture. And all 4 of these galaxies are actually gravitationally interacting. We can see those tidal streams a little bit here that we mentioned with the previous example galaxy. They're all literally intertwining themselves as we speak in space. So as we watch these over time, we should be able to see some changes. Maybe not on like short time scales, but on tens or hundreds of year time scales, we can see a little bit of a change in the structure of these galaxies.
Valerie, there's a question in the chat feature.
Oh, yes.
Why quintet when it's 4?
Yeah.
Doesn't like quin quattro 4, or is quin a different number? I was thinking like that, doesn't that just translate to 4, or am I being silly about that?
I believe quintet is 5.
Is it 5? That's a great question. Maybe they are referring to, possible that this is like another galaxy. I'll have to check, because usually when I see, oh, you know what? Maybe this one here, they're probably referring to it as a double galaxy here, because I can see kind of 2 bright centers now that I pay a little bit more attention to it. So I bet that's what they're saying, is that this one here is probably a direct collision with this one, and they're still counting this as 2 separate galaxies, even though they're actually merging. I was thinking like quattro 4, but you're right. Yeah, quintet 5. Thank you. Thank you for that. All right, so this is my last picture, and then we're going to wrap things up here. So maybe you have seen the Hubble Deep Field before. It has been talked about a lot, and there are now many different versions of the Hubble Deep Field. So I wanted to show you this one because this one doesn't get a lot of press. These Hubble Deep Field images, what we do is we point the Hubble Space Telescope at a patch of sky for a very long time, multiple days straight. And we stare at that patch of sky, let all of the light collect on the telescope, stack and add images together, and basically get a really deep view of the night sky. And what we see in a picture like this then is not a bunch of stars, but a whole bunch of galaxies. So almost every dot in this picture is not a star, but a galaxy. Even the teeny tiny ones in the background there are actually galaxies. They're just so small and so far away that we can't see their structure. We just see them as teeny little dots in the picture. And some of the ones that are a bit closer, those are spirals and ellipticals. We can see their structures a little bit better. So this one is the ultraviolet Hubble Deep Field. It includes ultraviolet images along with the visible light ones. And when you look at the picture and you see blue, like these galaxies that are glowing really brightly at bluer wavelengths, those highlight the star formation and the young galaxies and potentially starburst galaxies, more collisions in outer space. So pictures like this just go to show that literally our universe is filled with galaxies. We think that no matter where we look in every direction, there are galaxies everywhere, equally distributed throughout. We have taken multiple Hubble deep fields in different patches of the sky, and we have seen essentially the same thing every time. No matter where we look, equal, amazing distribution of galaxies across the whole night sky. So these pictures are spectacular, and they really help us understand the density of galaxies, the different types of galaxies, and help us understand more about how the universe has changed in time. Because the further away we look, the further back in time we are seeing these galaxies. So we're really seeing not just the universe as it is today, but as the universe was billions of years ago in this picture, which is kind of a cool concept to think about. So I'm going to kind of wrap up the talk here with just a mention of something that happened to Hubble recently, and then how Hubble's mission will ultimately end. You may have heard in the news back in June and July, it was the hot topic, that Hubble was kind of broken. So on June 13th, Hubble basically shut down. It has some fail-safes built in where if something goes wrong, the Hubble will just kind of close up shop, turn off, and send some alerts down to Earth that says, something isn't working right. I'm going to shut everything down so that I don't cause more damage. So basically, the payload computer controls everything on Hubble. It stopped working, and it sent those messages of something is wrong. And scientists and engineers spent a month and a half trying to figure out what was happening. They tried to troubleshoot and send some commands back and test some things out. And ultimately, what they figured out is that there's a problem with the main power control unit, the PCU. And you can see a picture of one that's actually in a museum. This is one that they used for training when they were going to potentially repair it years ago, but now you can actually go see it. I believe it's in the Smithsonian. But they figured out that it was this power control unit that essentially was sending incorrect voltage to the different instruments on board. And that triggers Hubble to shut down, because you don't want to send, too much voltage or too little voltage. Things won't work properly. So after a month and a half, they deduced that that was the problem. And thankfully, there are lots and lots of backup systems on Hubble. So they were able to turn to the backup PCU, which was on board, and basically use the backup computer and the backup power system. And Hubble is now back up and running as of early August. So things are going smoothly now. Science is happening again. Some scientists, unfortunately, did miss their time to observe what they were hoping for this summer, but their observations, if they can, will ultimately get rescheduled. So as long as Hubble continues to work, they'll be good to go. But eventually, Hubble is going to have to come down. We hope that Hubble will last until 2025. The instruments on board in general have an 80% reliability up through 2025, which means that we're pretty confident that things will continue to work. Although we have had to switch to the backup system now, which means that we're, if anything goes wrong there, we're kind of out of luck. We can keep Hubble operational at the very latest until about 2030, 2031, because when we would go up and repair the Hubble, we would latch onto it with the shuttle and we would boost it up a little bit because its orbit just naturally degrades ever so slightly. There is some tiny, tiny bit of atmosphere up there that creates drag that pushes it down towards the Earth. So without boosting Hubble again, it will ultimately crash down to Earth. Not tomorrow, it's not going to go out of control, but we do have to keep in mind that when we bring it back down, we want it to be a controlled deorbit. We don't want to just let it go. So we can leave it up there safely until the early 2030s, but eventually what we'll probably do is send some sort of robotic spacecraft, doesn't have to be human controlled, up to the Hubble that will literally push it down towards the Earth, and we will let it burn up in the atmosphere. So you can see a picture, not of the Hubble, thankfully, but of another satellite that was deorbited, and then you can just kind of see it, burn up. It'll look like some really cool shooting stars in the sky for a short evening. So that's ultimately what's going to happen to Hubble, but fingers crossed, we get at least 4 more years out of it. But until then, you can spend hours on the internet checking out more beautiful images of Hubble. The 30th anniversary website is there, lots of great things to look at, including a really fun activity where you can type in your birthday, not the year, just the month and the day. And the website will tell you everything that Hubble looked at on that day over the years. So you can see what Hubble was staring at on your birthday every year that was up. So that's what I have for you guys. I'm happy to hang out a little longer to answer more questions. I also put my email on the slide there. So if you think of something later, you can always shoot me an email. But thanks. I hope you enjoyed looking at some of the Hubble pictures that maybe you hadn't seen before.
Right.
Yes, thank you. Thank you. This was fascinating. And we'll open it up for questions.
I have a question.
Okay.
Valerie, throw out a few facts and I'll let you bring them together.
Sure.
First fact is, you've already mentioned Hubble was extremely expensive.
Mm-hmm.
Second fact, as far as I know, while we're trying to keep Hubble alive as long as possible, we do not plan a successor to it in the visible light.
Correct.
And the third fact is, does that mean that today, with today's technology like adaptive optics, that we can get a lot of the same images with ground-based systems?
Yes, that is all correct and all great points. So you are correct that there is no planned successor to the Hubble Invisible Light. We do have James Webb launching, hopefully, fingers crossed, in November of this year. We've already spent over $12 billion on that. It hasn't even launched yet. But that's a whole nother hour and a half long lecture for another day. But that will focus on infrared light. So it will be an amazing successor, but not identical to Hubble. And you are right, with adaptive optics today, we can get pretty much as good quality as the Hubble Space Telescope can provide just by using large ground-based telescopes with optical systems that allow us to essentially cancel out the atmosphere. But that leaves the potential for, if we can do just as good as Hubble on the ground, that means we can do even better in outer space. So if somebody wants to invest in a successor to Hubble, it's totally worth it, because the technology we have now is 1,000,000 times better than it was in 2009. So the pictures will only get better. But right now, there is no big visible mission planned by NASA.
We have a question from Ted. He asks, can you explain the color we see? Is it accurate as we understand color, or is it artificially generated to categorize what we are seeing?
So many of the pictures that I showed you were true color. So if your eyes were as big as Hubble and the telescope was as sensitive, the reds would be red, the blues would be blue, and so on. With the Hubble Space Telescope, we do utilize filters, and in some cases, we're looking at like a very narrow range of the red color, not just all of the red together. So we can kind of enhance the colors more than our eyes would see. But in general, what I showed you were true colors. That's not the case for all telescopes or all Hubble pictures. Sometimes they use, basically they just pick a color to use artificially with the computer generated images. But what I showed you was pretty much natural coloring.
And I don't remember now what it was called.
That's okay.
Did the scientists know to point Hubble at that, or was it just luck that they got a picture of something happening?
Yeah. Well, if you're thinking about that light echo, where that one, kind of changed over time, we saw something happen on the ground. With a ground-based telescope, we saw the star get really bright. We wanted to learn more. And then the Hubble Space Telescope was pointed at it. So it's kind of a 50-50 shot for images in general. Sometimes we catch something with a smaller telescope that looks peculiar, and then scientists will say, hey, can we point the Hubble at it? It would let us figure out what's going on. But often we have some clue that, that galaxy might be interesting, or that star cluster might be interesting. And we plan ahead of time to look at it and learn the science after the fact. So we don't, know exactly what we're going to see necessarily. But it's kind of a mixture. Sometimes we know something really exciting is going to happen, and sometimes we're just pleasantly surprised.
And for instance, if something is 250 million light years away, I don't know how to explain. Something was being formed, say 250 million light years away. What stage is it at today?
Well, that's a great question. So when we say that a galaxy or a star or something, well, really more a galaxy, is 250 million light years away, we're seeing it as it was 250 million years ago, because we had to wait for the light to get to our eyes. So we don't know, and we have no way of knowing exactly what it looks like today. I mean, we can make predictions based on how we think stars form and galaxies evolve, but I can't tell you what that galaxy looks like today. I can only tell you what it looked like 250 million years ago. That's all I can see.
I would like to thank Valerie because my granddaughter is majoring in astrophysics in college.
Oh, great.
And I've been trying to read everything I can and watch everything to try to understand exactly what it is. And this program has helped so much. So thank you, Valerie.
You're very welcome.
Based on what has been observed thus far, how many galaxies are we aware of?
So we have physically seen maybe a few thousand, maybe 10,000 galaxies, give or take. I don't even know if we have a full number of exactly how many we've observed so far. But we extrapolate and make an educated guess that there are literally hundreds of billions of galaxies out there. You know, we can look at an image like the Hubble Deep Field and literally count the dots, right? You could probably get 1,000 dots just from that picture alone. And maybe we have looked at, you know, a few thousand other galaxies up close, but we've only seen a small handful of what we believe to be out there. If the Hubble Deep Fields are correct, there's literally that many galaxies in every corner of the universe. So hundreds of billions total. We'll never be able to actually see every galaxy that exists.
I have two questions here from Ted. Are there plans to send up a second Hubble when the current one stops functioning? And the second question is, the data sent back from the Hubble shared openly with scientists around the world so that the broader scientific community can conduct its various research without regard to political borders or academic institutions?
Yeah, those are great questions. So we won't be replacing the Hubble. As we said, there aren't any plans to replace that at the moment, at least not with an optical-based telescope, but maybe in the future, there's always potential. And Hubble data is publicly available. Usually the astronomers get 6 months to a year with the data proprietary just for them, which allows them to do some of their science before anybody else can get their hands on it. But you can go online to Hubble's website and search the database for anything you want. It may not be the most user-friendly if you don't have a scientific background and understand the types of images that come back, but anybody can look at and search for Hubble Space Telescope. It is freely available to any astronomer around the world. We share everything.
Okay. Another question, aren't there galaxies beyond which those we can observe, meaning where there is no measurable light?
Yes, so this gets into the tricky thing of our observable universe versus the true universe. So because light travels at a finite speed, we can only see so far. We can only see 14 billion light years in one direction or the other. But early on in the formation and evolution of our universe, space itself actually expanded faster than the speed of light, which means that if you think of the universe as a bubble, which is not the greatest way to think about it, but bear with me here. You have a sphere that you can see out to the edge of the bubble, and then there's still more bubble beyond the inner edge that exists, but the laws of physics won't allow us to see beyond our inner edge. The light wouldn't be able to travel fast enough to ever get to our eyes. So it is very possible that there are galaxies outside the observable universe that we will never be able to see because we're limited by the speed of light.
I just want to thank you, Valerie. Really fascinating talk. And I want to thank everyone for joining us here. Hope to see you at our next lectures, and have a good evening.
Thank you. Have a good night,
Thank
everybody.
you.